Let X be the set of ordered pairs x and y, both integers, such that x squared over 8 plus y squared over 20 is less than 1, and y squared is less than 5x. Three distinct points, P, Q, and R, are randomly chosen from X. Then the probability that P, Q, and R form a triangle whose area is a positive integer is a bunch of options here. 71, 73, 79, or 83, all divided by 220. So what I might want to do here is I want to figure out exactly what the region bounded by these two curves is. We have an ellipse, and we have the intersection of the interior of an ellipse and some region below a parabola. No. What is that? That'll be some region below a sideways parabola, or contained within a sideways parabola. And then it might be nice to figure out exactly which ordered pairs there's a lot of, let's figure out which ordered pairs are actually in this set. So if I plot the function y is equal to square root of 5x, well, what is the largest value of x that I need to consider? X squared is certainly less than 8. So root x is less than root 8. So this says that y is less than square root of 40. Right, I have some kind of region like this. I also have below the region, I'm looking at all the grid points inside of here. Oh man, this is... Oh, it's not, y doesn't go up to 40, it goes up to root 40. But I also have y squared is less than 20. So y has to be less than the root of 20. Like, we have an ellipse here, and we have this parabola, and we're looking at the area that's kind of in between them. This is certainly not to scale, right? The horizontal and vertical scales are pretty different here. Oh, this should be the root 8, not 8. Doesn't really matter. And we're looking at all of the grid points in here. So we're choosing 3 of these at random. asking what is the probability that the area is a positive integer. Okay, well, I don't see a nice way of doing this. You know, given that, given the denominators in this problem, all of them 220, am I supposed to believe here that there are 220 ordered pairs within this region? Oh wait, no, but we're choosing 3 points. 3 distinct points. So perhaps there are 220 distinct ways of choosing 220 ways of choosing 3 distinct points. Still potentially a lot of points, right? Okay. Should I just start listing the ordered pairs? Maybe that's, honestly, maybe that's the way to go, because we know, oh, you know what? That's got to be the way to go, because x is only, oh my gosh, why did I write this? It's x is less than the root of 8, not the root of x. Okay, here's what we're going to do. Here's what we're going to do. Okay, when x is equal to 0, there are no values of y that satisfy the second inequality. Okay, so when x is equal to 1, we need y squared over 20 has to be less than 1 minus 1 over 8, and y squared is less than 5. So what values could work here? Y could be equal to, I'm only going to list the positive values, or non-negative values. 0, 1, going to be equal to 2. 4 over 20 less than 7 over 8. Is this true? 2 over 10 less than 7 over 8. Yes, is this true? Okay, so let's list all the values. Why not? Okay, so there are 5 ordered pairs there. X is equal to 1, and y can be one of those 5 numbers. If x is equal to 2, I need y squared over 20 is less than 1 minus a half. And I need y squared is less than 10. So my only candidates here are y is 0, 1, 2, or 3, along with negative numbers. But I need y squared less than, y squared over 20 less than 1 over 2. So again, this is y squared less than 10. So y is going to be equal to negative 3, negative 2, negative 1, 0, 1, 2, 3. If x is equal to 3, we have y squared less than 15. But then we also have y squared over 20 is less than 1 minus 9 over 8. Okay, so that's not possible, right? Yeah, all right, so there's fewer ordered pairs than I expected. There are 5 plus 1, 2, 3, 4, 5, 6, 7. So there are 12 ordered pairs. So the number of distinct ways of choosing are 12 choose 3. What is this? This is 12 factorial divided by 3 factorial times 9 factorial, which is 12 times 10, 11 times 10 divided by 6, which is 2 times 11 times 10, which is 220. So that's where the denominator is coming from, 220. Now, what are the conditions I need on these points for the area to be a positive integer? Okay, well, I need them to have I don't know why I drew the axis in such a way, because something more like this. X can only be equal to 1 or 2. When x is equal to 1, I go from -2 to 2. And here I go 1, 2, 3, 4, 5, 6, 7. So if I make a triangle, so clearly the values of x, I can't have all 3 points on the same vertical thing here. The horizontal width of this triangle is always going to be 1 or 0, right? And I want to eliminate all the ones that are 0. So the horizontal width is going to be 1. And then I need the vertical height to be even, because the area is going to be the width times the height divided by 2, right? So for example, this is a valid triangle like that, as is this one. Maybe I just count all the triangles that work. If I take this triangle and consider all translations of this one that work, there's one here, 2, 3, 4. So that'll give me 4 triangles. And then symmetrically, I have this one, 2, 3, 4. Okay, so I've done that triangle. And that triangle. Now let's do the same sort of orientation except twice the height. 1, 2, 3, 4. So there's that one, and there's the one shifted up by 1. So that'll give +2, +2 for the taller version of that, and reflected like that. Okay. Now I need, this is where the vertical side is always here. Now I need to consider when the vertical side is over here. So I've got this, and I can shift this up twice. And I can flip it upside down. It gives me another 2. So what have I got there? That's what did I do? 1. Oh wait, it's not going to be 2. It's going to be 3, isn't it? I also have that, and its flipped version. This is not nearly large enough. Did I miss, when x is equal to 3, did I miss... Well, the area could... Oh no, it says the area is a positive integer, so we're ruling out an area of 0. What is this number equal to? 8, 9, 10, 11, 12, 13, 14... This is 20. Why am I missing so many of the triangles? Oh, shoot. This also works. Okay. This is all of the right triangles. But then I also have, how many of these do I have? 5. Plus 3. Okay. Will there be more? 1, 2, 3, 4, 5, 6, plus 1. I'll flip them the other way. There's a better combinatorial way of doing this, isn't there? Right? Yeah, for sure. Okay. I don't want to keep counting this. This will work, but it's too much counting. I'm going to do this a better way. Let me explain what I'm thinking now. If I choose any line segment of length 2 here, and then connect to any point on the right side, like that, this triangle will have an area of 1. Okay, so this line segment has 7 points to connect to. That all work. This line segment similarly 7 points, and this line segment 7 points. So that's 21, corresponding to a length of 2 on the left. Then if I do a length of 4 on the left, that'll give me another 7 points. So this corresponds to 4. A length of 4 on the left. And then if I do something on the right, so that's the line segment of length 2. There are 5 triangles I can construct from that one. And there are 1, 2, 3, 4, wait, 1, 2, 3, 4, 5. 5 times 5, so plus 25, or 2 on the right. But to have a length of 4 on the right, 1, 2, 3, 4. That'll give me another 10. No, 15. Let me make sure I counted this correctly, just a minute. 1, 2, 3, 4, 5. Yep, that's 25. So this line segment of length 4 will have 5 possible triangles that work, 1 for each point on the left. And there are 1, 2, 3. And then this is a line segment of length 6, and all of them will work. It's 5. Okay, so what do we have here? 40 plus 21, 61 plus 12 is 73. So there are 73 triangles that work, and that's answer B. Okay. I don't want to go back and check my work and make this video too much longer. This was, I guess in the end, kind of a cool question because combination of a lot of things. I really had no idea what my approach was going to be at the beginning here, and just sort of trying things ended up working out. What were the key parts here? Of course, recognizing that the two equations, or the two inequalities, give an ellipse and a sideways parabola. I don't know if that worked too much because I ended up just brute forcing to figure out every single possible point that could be in this set. But it worked out to be significantly fewer points than I thought. Of course, computing the total number of ways of computing triangles here. Fairly straightforward. 12 choose 3. There we go. Yeah, the fact that there are only 2 different values of x helps immensely here. And counting all the triangles would have worked, but it would have taken ages because I would have had to eventually be counting triangles that are congruent to something like this. So I'm happy that I realized it's essentially just kind of a combinatorial thing. Just, clearly, if I take that as the vertical segment, then choosing any one point on the right-hand side will create a triangle with integer area. Yeah, so that's my answer, 73 out of 220. If I find a mistake or if I have more to say, I'll put it down in the description. Thanks for watching.